This is Paris course number 88, and today we're talking about Zimmerman airfoils. So in a couple of podcasts ago, I was talking about Zimmerman airfoils there, and you may not have heard of them because they are fairly unique and somewhat rare. However, they're becoming less rare now that MAVs are a huge industry, a huge field. And so the Zimmerman airfoil is not just a profile, but also the plan form. So the difference being that the profile is like if you take an airfoil and you cross section it, that's the profile. If you take the airfoil and you look at it from the top view, that's the plan form. So Zimmerman airfoils both have a fairly unique profile and plan form. And to look into the aerodynamic properties of these wings, we're going to look at a paper called Lift, Drag, and Pitching Moment Performances of Different Wing Profiles for MAV Wings. And this is an open access paper. You can find it in the link in the description. And I detail 3 different Zimmerman profiles, which we'll go through, and how they affect the lift coefficient, drag coefficient, and the moment coefficient. So starting off, MAVs have been defined to have a maximum length of 6 inches, so 15 centimeters, with a gross takeoff weight of 200 grams or less, so about 40% of a pound. MAVs fly in low Reynolds number regimes, so about 100,000 or less. That's because they are so small. So the only way to get high Reynolds numbers is to go really fast, which obviously MAVs usually don't have the power to do. A thin cambered plate airfoil with a Zimmerman wing platform is the most suitable wing for such an MAV application, since it can induce better lift coefficients compared to the flat plate airfoil configurations. So we'll get into, you'll see why later on, but generally speaking, a flat plate, you can only really pitch to a couple of degrees before it separates, whereas a Zimmerman airfoil, because it is fairly wavy on top, you can pitch to a much greater angle of attack and still maintain lift, as we'll see. So generally, a thin and cambered airfoil geometry can be designed based on a certain polynomial order. So this polynomial order method provides freedom for the airfoil designer to choose the suitable airfoil shape for the MAV. So in other words, the cross-section of the profile, you can then just model with a polynomial, whether that's, obviously a linear one won't be that good, but you could do a quadratic, cubic, quartic, or higher. In this one, they're looking at cubic, so to the third order. In this work, an aerodynamic study on MAV wings configured with different wing profiles based on the third order polynomial equations have been carried out. This study focuses on the aerodynamics performance of 3 proposed wing planforms designed with different third order polynomial equations. And they look into the performance with CFD using ANSYS CFX. Now, one thing that I want to mention here, they say it's analyzed through the virtual wind tunnel simulation. Now, I want to talk about this term particularly because you can use it correctly and incorrectly. So a virtual wind tunnel does not necessarily mean you're just doing regular CFD. A virtual wind tunnel generally means that you have to model the wind tunnel. That's why it's a virtual wind tunnel, because technically wind tunnels are not really, they're not the be-all and end-all. They're actually designed to mimic real life. So if you're doing CFD and you're trying to mimic real life as well, you're not technically mimicking a wind tunnel. You're mimicking real life, and the wind tunnel is also mimicking real life. Hopefully, both of them, all 3 of them, line up very well, but they could be very different depending on the quality of your setups. So if you're doing a virtual wind tunnel, technically you do have a wind tunnel present. You're trying to mimic some sort of wind tunnel. If you're not doing a wind tunnel, then I guess you're not really doing a virtual wind tunnel, are you? You're doing real life. So the MAV wing modeling, let's talk about this. In figure 1, they have the planform, and as I mentioned earlier, you have from the top view, you have this shape is like, effectively imagine like an ellipsoid or an elliptical shape, and you cut it in half, and then you just like get the back half and you just draw a line across the leading edge. That's effectively what the Zimmerman airfoil looks like. The edges are rounded a little bit, so it's not nearly as sharp, but that's the general shape. Now for the profile view, it can be really anything, but in here they have it's sort of like a sine wave. So if you think of a trigonometry sine wave, where it goes like that curvy shape, and then you sort of make the amplitude a bit lower, like smaller, that's what it looks like. That's the profile shape. So you're going from the leading edge to the trailing edge. That's a Zimmerman airfoil. And that's what they're looking at here. So based on previous work, a Zimmerman wing planform with thin airfoil profiles were chosen for this study, as shown in figure 1, which they had as above. I was explaining what it looks like. This is because the Zimmerman wing planform already has been shown to be compatible with MAV applications. the main thing is that they fly at low Reynolds numbers, but you need to have fairly high lift coefficients. And Zimmerman airfoils have shown this, and we'll see it again in this paper here. For this study, 3 different profiles, known as Profile 1, Profile 2, and Profile 3, produced by 3 different third-order polynomial equations are proposed here, and they have figure 2 showing these profiles. So Profile 1, they all have effectively a sine wave shape to it. And Profile 1 is much more squashed, the amplitude is very low. Profile 2 is somewhat thicker, and then Profile 3 is very thick. But you need to remember that these profiles are really just flat plates, but that are bent in a sine curve fashion. So that's what they look like. The main characteristics for each wing profile are given in Table 1, and basically all wings have similar wing characteristics in terms of the chord length, wing area, and aspect ratios. So the chord length is 150 millimeters, so that's 6 inches. That's the most that you can have for a MAV by classification. The wing areas are around 35,000 or 36,000 square millimeters, and the aspect ratios are about 0.63, which are very low. So each wing was tested at a similar velocity of 10.074 meters per second. And this is because it gave a Reynolds number based on the root chord of 100,000. The main differences between the wings are the profile equations, so the third-order polynomial equations, to develop the wing profiles. Resulting from the profile equation differences, each wing profile induced a difference in the camber percentage. As I mentioned earlier, Profile 3 was very aggressive in terms of its styling. It has a very high amplitude, and the camber percentage for this is 15% based on the chord. Profile 1, I mentioned, was much thinner and sleeker. Its camber was only 3.8%. Profile 2 somewhere in the middle with 7.5%, so effectively they doubled the camber each time. Now, in the aerodynamic simulation results, they talk about the lift coefficient. So they simulated these airfoils in CFX, as I mentioned, which is a CFD package in ANSYS. That's a Navier-Stokes solver, by the way. If you want to learn about lattice-Boltzmann equations and those solvers, check out podcast number 85 and 86, which I go through some of that there. If you don't know what lattice-Boltzmann is, then definitely check out those podcasts because they're really good, if I do say so myself as well. So the lift coefficient distributions. In figure 5, we have the angle of attack on the x-axis and the lift coefficient on the y-axis, and we have all 3 profiles plotted. Generally, each wing induced similar lift coefficient trends throughout the angle of attack range. The lift coefficient for each profile increased with increasing angle of attack up to the maximum angle of attack, which after that stall occurred, which makes sense. Each profile induced the maximum lift coefficient at the stall angle of attack before it tended to degrade in magnitude in the post-stall angle regime. So in other words, they followed a very typical airfoil behavior where when you increase angle attack, the lift coefficient increases up until a certain point, then you get flow separation, and then you get stall. And the stall patterns for these, I should mention, are quite gentle. So Profile 1 and Profile 2, the stall doesn't dramatically drop. In fact, it only drops maybe 10% when you increase the angle of attack a lot. So that's quite nice to know. Profile 3, it has a very steep stall, but not nearly as bad as like a 0012, for example, which is a quintessential airfoil. The stall for this particular Profile 3 drops by about 40%, 35% over a 10-degree angle attack range. So it is fairly subtle still, but compared to the other 2 profiles, it is much more aggressive. So based on the maximum lift coefficients, so let's talk about these. Based on the maximum lift coefficient analysis taken in the pre-stall regime, so between 0 degrees and 30 degrees. 30 degrees is approximately where all 3 profiles sort of stalled. On average, Profile 3, which is the most aggressive, induced a 20% higher lift coefficient compared to Profile 2 across the entire angle attack range. While Profile 1 produced the lowest lift coefficient among the wing profiles, with on average only about half the lift coefficient of Profile 2. So that's interesting, even though Profile 1 had about half the camber of Profile 2, and that effectively corresponded to half the lift. Profile 3, though, had twice as much camber as Profile 2, but it didn't produce twice as much lift. It was only about 20%, so we're starting to get to the saturation point. In terms of the angle attack, the stall angle attack, Profile 2 has the greatest with 35 degrees. This is followed by Profile 1 and Profile 3 at 32 and 30 degrees respectively. So that's interesting. So this is an interesting phenomenon that's going on. Profile 1, because it is so sleek, is acting more like a flat plate than the other 2, which means that the angle of attack for stall is going to be lower because of that. Profile 3, though, because it's so thick, effectively, the camber is so extreme, the stalling attack also drops because of that. So profile 2 is sort of like in that Goldilocks region. Based on these stall angles of attack, it means that profile 2 has at least an 8.6% greater stall angle compared to the other two profiles. The analysis of the maximum lift coefficient shows that profile 3 has the greatest maximum lift coefficient with 0.75. Profile 3 produced at least 22.9% higher lift coefficients compared to profile 2, which the maximum lift coefficient was 0.6 only, and profile 1 was only 0.27. So the maximum lift coefficient for profile 1, which was a very thin airfoil, was 0.27, which is pretty terrible compared to the other two profiles. But compared to a flat plate, it's pretty decent still. So profile 3 has the promising advantages in generating better lift distributions, both in the maximum lift coefficient, the lift curve slope, and even in the stall regime, it's pretty decent still. Profile 3 shows huge advantages in the lift coefficient and the maximum lift. These advantages are expected due to the higher camber percentage found in profile 3, they say. So with the drag coefficient, which is now my favorite, I'm a specialist in drag coefficients. Figure 6, they have the drag coefficients plotted for each of the three wings. And they say that generally each wing profile produced similar drag coefficient trends throughout the angle of attack range. The drag coefficient for each wing profile slightly decreased at low angles of attack, so between -5 degrees and 3 degrees, which is very common for airfoils. That's where you're going to get the lowest drags. For positive angles of attack, the drag coefficient increased monotonically with the angle of attack, which makes sense. This is what's called a drag bucket. So when you have 0-degree angle of attack, typically airfoils will have the lowest drag around this point. And if you go left or right of this point in the x-axis, you're going to get an increase in the lift, in the drag coefficient, generally speaking. Now, for most airfoils, you might be within like -3 to +3 range, and then once you go outside that, they'll start to increase dramatically, depending on the camber and the thickness. But generally around 0 degrees is when you're going to get the lowest drag coefficient. And then you're going to get to a point where stall starts to kick in, and then the drag coefficient is going to jump really high. And that's because you get a huge drag coefficient, a huge pressure drag coefficient, which is due to a much greater pressure at the front of the airfoil compared to the back, which produces a force. So that's what we're seeing here as well, the drag bucket. And when we were approaching stall, the drag coefficient increases. However, because the stalls were so soft, the drag coefficient did not have that jump that we'd expect for a thinner airfoil such as a NACA 0006 or a flat plate. So the drag coefficient results clearly show that each wing profile reaches the minimum drag coefficient at nearly the same angle of attack of about 0 degrees. By comparing the minimum drag coefficient, we can see that the profile 1, which is the thinnest one, or the least cambered, has produced the lowest drag coefficient among the wing profiles with a minimum drag coefficient of 0.000027. Now, this value I'm not too sure about. The reason why is because that's just really low for an airfoil. I mean, I don't even know any airfoil which is below 0.0001, let alone 0.000027. So I think maybe that needs to be checked. The other two airfoil profiles, they had minimum drag coefficients of 0.007 and 0.0257, and those are normal, like they're in the expected range. For profile 1 to have such a low drag coefficient is a little bit hard to believe. I mean, it shouldn't have much of a pressure drag, but still the friction drag should be fairly high, considering that it should be the equivalent of a flat plate, almost. So that's very low. I looked up the drag coefficient of a NACA 0006, which is a very thin airfoil, and it's the closest one in some respects to these airfoils, particularly profile 1. And the drag coefficient was still like 0.005. So it's still much higher than what they're reporting here. So I would be tentative about this value here, and I'd like to look into it more. They say, though, that this means that profile 1 induces almost 50% less drag at the minimum drag coefficient than the other two wing profiles. Now, technically, it's actually a lot less than that. It's less than 3%. Well, yeah, about 3% of profile 2, and then even less for profile 1, for profile 3, sorry. So again, I'm not too sure about that. But one thing that does make sense is that it does have a much lower drag coefficient than any of the other two profiles because it is thinner. It has a lower camber, I should say. So based on a comparative analysis on the drag coefficient conducted between angles of attack of 0 and 30 degrees, so this is the pre-stall regime, the results show that the profile 3, which is the most aggressively cambered, has consistently produced at least 57.5% higher drag coefficients compared to profile 2, while profile 2 has produced at least 80.9% higher drag coefficients compared to profile 1. It clearly shows that profile 3 has induced the highest drag penalty among the wing profiles. Such a condition is expected due to the larger camber percentage found on profile 3. So despite the profile 3 producing the best lift, it also produces the worst drag. And they said that this is also potentially due to the larger frontal area, which means that it has additional form drag. And form drag is an aeronautical term which combines skin friction drag and pressure drag. In this case, because it has a larger frontal area, they're talking about the pressure drag component of form drag. And also because it produces so much more lift than the other two profiles, the induced drag is higher, so the wingtip vortices are stronger. You can think of it that way. Now, they look at the moment coefficient as well. And the reason why the moment coefficient is important is because it tells us how stable the wing is. What we want is a negative moment coefficient, and the greater the lift coefficient, the greater the moment coefficient should be as well, the more negative it should be. The reason why is because if you think about when you're flying around, if you're producing more lift and as a result you have a greater pitching up moment, it means that the airplane wants to pitch up more and more the more lift you produce. That becomes dangerous because now you're reaching the stall angle of attack. So what you want is the higher the angle of attack, the higher lift that you have, the more your nose of your aircraft wants to go down to reduce the lift that you're producing, so that's more stable. You want to approach like 2 degrees, perhaps your cruise angle of attack. That's safe. If your moment coefficient compared to your lift coefficient, if you plot it, is a positive slope, it means that your airplane is unstable. Now for this, these profiles, they have the moment coefficient plotted on the y-axis and the lift coefficient plotted on the x-axis, and they show that it's a negative slope for all three profiles, which is really good. It means that these profiles are very stable. And interestingly, they all have about the same slope. Profile 3 has the best negative slope, but then profile 2 and profile 1 are still pretty good. And the more lift you produce, the more negative the moment coefficient becomes. So that's very good. Now I looked up the moment coefficient for a NACA 0006, which I mentioned earlier, is a comparable airfoil to these airfoils to some extent. And the moment coefficient for those airfoils are terrible, like they're all over the place, whereas these ones are very good. So this shows that in terms of this airfoil, the NACA 006, these Zimmerman airfoils are much better. And the reason why I picked them NACA 006 as well is because they also produce similar lift coefficients at angles of attack comparable to these. So if we go to the lift coefficient graphs, we saw that profile 3, which was the most aggressively cambered wing, produced a maximum lift coefficient of about 0.75 at a Reynolds number of 100,000. For the NACA 006, the maximum lift coefficient was about a 0.7 to 0.8 again at Reynolds numbers of 100,000 as well. So they're very comparable, and that's the maximum that it produces. And the drag coefficients were about similar as well. So what this means is the Zimmerman airfoils are very good at producing lift at low Reynolds numbers, and they can also they're also much more stable. So they also have fairly agreeable stall characteristics, where you don't have this massive drop off in lift once you reach a certain angle of attack. It's more gentle. So these are all very beneficial aerodynamic properties of Zimmerman airfoils and how they are different to most other airfoils. So for most other airfoils, when you reach the stall angle of attack, the lift will reduce dramatically. You'll have some airfoils are stable in terms of their pitching moment, others are not. And also the lift being produced at low Reynolds numbers are fairly low for most airfoils, and you also result in a very low stall angle attack. So, for example, in NACA 0021, I think at like 100,000 Reynolds number, the stall angle attack is like 13 degrees, something like that. It's very low. Whereas these ones, the stall angle attack are around 30 to 35 degrees. So you can go to a much higher angle attack, and that means it's more stable. You can have safer margins. So that's how Zimmerman airfoils are different to regular airfoils. And in conclusion, Profile 3, which was the most aggressively shaped profile, produced the greatest lift coefficient. However, it also produced the greatest drag coefficient, generally speaking. So whether that's the most efficient airfoil or not, we don't know. They didn't plot, unfortunately, the lift to drag ratios, which are very beneficial. Profile 1, which was the least aggressively shaped profile, produced the lowest drag coefficient, but also produced the least lift. And all wing profiles produced similar stabilities at low angles of attack. But profile 3 was far more stable at high angles of attack. So the more aggressive it was, the more stable it was at high angles of attack, at high lift productions. So that's the end of this podcast. Let me know what you think about Zimmerman airfoils, or if you know other airfoils that are comparable or even better for MAVs. And if you like this, also tell your friends, because they will be interested about Zimmerman airfoils as well. Because let's face it, it's a cool name, and that's what matters. And if you want to get better at theory and CFD yourself, check out our courses, link in the description. And if you want to learn about lattice Boltzmann method, as I mentioned earlier, check out podcast number 85 and 86. There are different ways of doing CFD. And I'll see you in the next podcast. Peace out, amigos.